Assume that you have divided up students in two groups, and in the one group the students get more gym classes and do more sport activities than the other group. And then you could ask yourself, does this affect the grade they get in mathematics? Then you could use confidence intervals to compare things like this. So we will look at how you can use confidence intervals to compare expectation values and probabilities and proportions for two different random variables. So let's start by comparing expectation values of two random variables. So let's say we have two random variables with unknown expectation values μ1 and μ2 respectively, and unknown standard deviations sigma 1 and sigma 2. Then we take a sample of each with the sample size of n1 and n2. And the mean of these two samples is these two, and we also get the sample standard deviations for these two. We assume that the means are normal distributed, either because x1 and x2 are, or because n1 and n2 are larger than or equal to 30. To compare the two groups, we want to compare the difference in expectation values. One can show that the confidence interval for this difference with the probability of 1 minus 2 alpha is given by this expression here. And for degrees of freedom for T alpha, we use the smallest number of n1 minus 1 and n2 minus 1. So let's take the example with two groups of students having different amount of gym and sports activities on their schedule. So assume in group 1 we have 45 students with more physical activities. And in group 2 we have 50 students with normal or regular physical activities. Assume that the two groups have these means in grades in math, and with these two standard deviations. Then can you with 90% probability conclude that the expectation values of these two groups are different, meaning that the grades in math are different for the groups having more physical activity and those having normal physical activity. To do that, we want to examine the difference in expectation values of the two groups. Since both sample sizes are larger than or equal to 30, with both means are normally distributed. The degrees of freedom are 44 for this group, 49 for this one, so the smallest one is 44. Then the confidence interval with 1 minus 2 alpha equal to 90%, and degrees of freedom 44 gives the alpha equal to 1.68 according to the table, where alpha is 5%. Then the confidence interval for this difference in expectation values is according to this expression here, and with our numbers put in, given by this one here. And here we just express the interval in this alternative notation, where plus and minus gives the two endpoints of the interval, which can be simplified to this, which is the same interval as this. We see here that 0 is not part of this confidence interval. That means that the difference in expectation values equal to 0 is not part of this confidence interval, meaning that expectation 1 equal to expectation 2 is not part of it. So with 90% probability, these two are not equal, meaning that having more physical activities on the schedule has affected the grades in mathematics with 90% probability. And also note that the difference is larger than or equal to 0 here for this confidence interval, which means that expectation 1 is larger than expectation 2. So more physical activity gives larger expectation value than for normal activity. So physical activity in this case have a positive effect. The example chosen here is fictive, but the principle here is how you can compare two groups using confidence intervals. Now instead let P1 and P2 be two unknown probabilities or proportions for two groups. And we have taken sample sizes larger than or equal to 30 for both groups. And that has given the estimates for P1 and P2 based on these samples. For the difference here in probabilities or proportions, one can show that the confidence interval with probability 1 minus 2 alpha is given by this expression. And here, again, we use the alternative notation for interval. So these two are the endpoints of the interval. And let's see an example how we can use that. Let's say a researcher have come up with a method to help pupils with read and write difficulties. They tested the method on 100 pupils, and 11 of those, after trying the method, had read and write difficulties. Then in a group of 1,000 pupils that didn't test the method, 130 of those had the difficulties. Assume that we want to know with 90% probability if this method has been successful. Then we're looking for a confidence interval with 90% probability, which give a set alpha with 1.645 according to the table. If this is group 1, then this is the estimated proportion of pupils having difficulties in that group, equal to 13%. And the group 2, that is those using the method, 11% had difficulties after the method. Which of the groups we choose to be 1 and 2 doesn't matter. Then if we put into this confidence interval, we'll get the following. And this can be simplified to: since 0 is included in this interval, we cannot be sure that the method has had an effect. If we want to conclude that it has had an effect, then what probability should we choose instead? If this one would have been 0.02, then 0 would just be on the border of being in this interval. And that corresponds to the maximum probability we can have. And for this one to be equal to this here should be equal to 0.02. So we need another value of set alpha. And when this is equal to 0.02, we have the corresponding set alpha. And if we divide both sides by this and calculate, this is equal to 0.61, which according to the table corresponds to this alpha, corresponding to this probability, that is 46%. So we can only say with 46% probability that the method has had an effect. So we are really not that sure at all that the method has had an effect. If we want to say that, then we need to test it on more pupils.